This lecture, I want to briefly cover how an alternative approach to counting the electrons within a transition metal complex called the oxidation state method. Before I get into that, though, let's recap a and just kind of review a counting method for a nice complex to showcase this example. So there's this titanium complex with two trimethylphosphine ligands and then two CP ligands, where CP is cyclopentadiene anion. Okay, so with this attached, we can kind of make note that the complex has an overall charge of 0. If we count each of these, or if we count the total electrons in this complex, we would see that we have CP, which provides 5 electrons, PME3, which provides 2 electrons. So we have 2 times a 5 electron donor from a ligand, 2 times a 2 electron donor, and that gets us to 14 electrons from ligands. Titanium, being group 4, gives us, whoops, let me just have some parallelism here. 4 electrons from titanium. And that gives us a grand total of 18 electrons because we don't have to take into account a charge or anything like that. The alternative approach is the oxidation state method. So the neutral counting approach does this. What you do is you take the, you say that the total electrons is equal to this kind of sum. We have the electrons from the metal, we are aware of the oxidation state of the metal, but we don't take that into account. So we don't take that into account. So we take the electrons from the neutral metal and the electrons from the ligands, and then we add those electrons, then we subtract the charge. Now the electrons from the ligands comes with a little bit of an asterisk in that we say that monovalent interactions provide 1 electron of a contribution to the total electron count. And so those monovalent interactions can be combined with pi complexes, and pi complexes provide 2 electrons. But those monovalent interactions are important to note. They provide 1. So CP anion really, all 5 atoms are adducting to the metal center. But I like to think of it as 2 pi complexes plus 1 monovalent interaction. That allows me to go back and forth between the neutral counting method, which I just talked about, and the oxidation state method. So the oxidation state method does this. So the oxidation state method, I don't know why I wrote method. Maybe I'm too excited to talk about this. So the oxidation state method says that the total electrons in a metal complex is the electrons from the neutral metal and that's a plus, minus the oxidation state of the metal. This was something that we ignored previously. But after last lecture, we've recognized how to identify it. For example, if you have ligands that would otherwise be negatively charged on their own, we're probably balancing that negative charge with some positive charge in the metal center so that we get our overall complex having the charge that it's supposed to have, usually neutral. Okay, so we're now taking into the account the oxidation state number, but that's getting subtracted. We're going to add the electrons from the ligand. And if before we had an asterisk, now we have a double dagger. Okay, and then what we do is we is then when we consider the charge of the complex, that's actually ignored. So now we ignore the charge of the complex. This altogether gives us our total electron count. So our double dagger is that ligands, or actually let's go with this, monovalent interactions provide 2 electrons. Okay, so that's the critical distinction here. It's not only the oxidation state, it's also that the ligand count is changing, the number of electrons from ligands. Now, all of a sudden, people freak out because they have to rememorize a bunch of stuff. Well, all I'm saying is if it's just the monovalent interactions that actually increase by 1. Okay, I believe maybe I should check my notes on divalent and that sort of thing. I might do that while I'm taking notes over while you all are catching up. Okay, so let's go back to our complex again with titanium, PME3, PME3, CP, and CP. So the CP before had 5 electrons, but now it has 6 electrons. Maybe I'll make those X's in red. Add a splash of color, as they say. 6 electrons. Now, why are we at 6 electrons? Well, we have 1 monovalent interaction plus 2 pi complexes. 2 pi complexes provide 2 electrons each, but now the 1 monovalent interaction went from having 1 electron to 2 electrons. 2 plus 2 plus 2, or 2 plus 2 times 2, is equal to 6 electrons total. Okay, so the PME3s continue to be 2 electrons because they're Lewis bases. So we have 2 PME3s, which provide 4 electrons, plus 2 CPs, which provide 12 electrons total. So ligand electrons went from 14 to, that's super sloppy, 14 electrons to 16 electrons. Okay, so our electron count on our ligands from ligands is now 16. The neutral metal remains 4 because it's in group 4 of the transition series. And then our oxidation state, and we talked about this last time, with having 2 -1 charge CP ligands, we're going to have an oxidation state of +2, right? Because we have an overall neutral complex. And to make an overall neutral complex with 2 -1 charge ligands, we need to have the metal center having an oxidation state of +2. We need to subtract the electrons that were, think about it, another way to think about it is when we do this subtraction here, well, I should write +2 for the oxidation state. When we do this subtraction, we're kind of subtracting the 2 electrons that got us to that oxidation state of +2. Okay, so we have 16 electrons from the ligands, plus 4 electrons of the neutral metal, minus 2. 16 plus 4 minus 2 equals 18 electrons total. So between both these approaches, we should get the same answer. I don't have I just am not as much of an expert in just coordination chemistry to know the advantages of using one approach over the other. I just try to be fluent in both for the sake of you all. Yeah, so that's the oxidation state method. We're just kind of replacing charge with oxidation state, and then we're upping our ligands. I was going to take a quick second. I didn't want to screw this up like I've done before. Counting, got a nice little chart here. And sorry, if you want to be done with this lecture, you can. I just want to I had this beautiful slide. Here it is. Just want to make sure there isn't anything else that kind of trips us up. Yeah, so oh yeah, sure. So the other things that kind of get doubled from 1 to 2, and then from 2 to 4 are the other things that would otherwise be negatively charged. And so I should say that carbenes and carbines also double. Okay, so what that means is that for the carbene, this is when we had a metal that was double bonded to a carbon atom. In the neutral count approach, that was a -2, a 2 electron donor, because if we push both back, we get to -2. So this was 2 electron, but with the oxidation state method, it now doubles to 4 electrons. It's kind of like having 2 monovalent interactions, and so we have to double both of them. Similarly, a carbine, or metal is triple bonded to a carbon, that goes from neutral, where it's 3 electrons, you push each over to make a negative charge, -3 charge in the carbon, and so we call it kind of 3 monovalent interactions. That becomes 6 electrons in the oxidation state method. Okay, just looking through one. Okay, there's some weird ones that I'm not gonna have us worry about, but I can just touch on some the influence of the monovalent interactions being increased by 1. So if we look at eta-3 allyl, where the metal is adducted this way, that goes from 3 electrons to 4 electrons in the oxidation state method. And the reason why is because this is 1 monovalent plus 1 pi complex. Okay, and then the other monovalent ones to consider are just our standard, like halides, amides, that sort of thing. So I could have metal X, metal Nr2, metal Cr3, metal hydride, sure, and then metal alkoxide. All of these go from 1 electron in the neutral atom approach to 2 electrons in the oxidation state method of counting approach. Okay, so there's probably others out there, but the big thing is recognizing when you have monovalent interactions with your transition metal complex, those are going to increase, or you could just stick with one approach to the counting. I thought it was worthwhile mentioning both. Okay, that way, down the road, if you see somebody changing the count, just recognize there's 2 approaches. They're very similar. They just handle monovalent interactions differently in whether or not we subtract the charge in the complex or the oxidation state in the metal, but we should get the same answer in either case. Okay, so that'll do it for this lecture. We'll see you next time.